Fantastic. All right. Hello, everyone. So this is the next installment of the Stellar Seminars. And today we have Jeremy Rigney, who graduated University College Dublin with a Bachelor in Science, honors in Physics and Astronomy and Space Science. He's now the Eric Lindsay PhD Scholar of the Dublin Institute for Advanced Studies and Armagh Observatory and Planetarium. His research focuses on examining the simultaneous optical and low-frequency radio emission from M-dwarf stars to better understand their activity, particularly stellar flares and the search for stellar coronal mass ejections. These events could have huge impacts on the habitability of orbiting exoplanetary systems, obviously. So I'm very excited to learn what Jeremy has to tell us today. So without further ado, please take it away.
Thanks, Cameron. It's great to be here. Thank you for the opportunity to speak to you all today about my research. As you said, I'm a third-year PhD student in Dublin Institute for Advanced Studies and Armagh Observatory, and my research started off focusing specifically on the radioactivity of low-mass stars, but it's kind of evolved into the comparison and trying to better understand first solar radioactivity and then applying that to these low mass stars. So I'll be talking a little bit about the sun and how we observe it across the electromagnetic spectrum, and then how we apply what we learn from the sun to M-dwarfs in the search for stellar coronal mass ejections. So I will get started. Some of this may be overlap for some people. I know a lot of you here are solar physicists. So I'd like to start by talking about the sun, our nearest star. It's a fairly small G-dwarf star, main sequence star, and it undergoes periods of activity over 11-year cycles. And this activity is often characterized by solar flares and coronal mass ejections. And we have the benefit with the sun being so close that we can observe it across the full spectrum from X-ray and EUV, optical up to radio waves. So to show what the sun looks like at EUV wavelengths, extreme ultraviolet, we have the AIA Atmospheric Imaging Assembly instrument on board the Solar Dynamics Observatory. And observing this at various different wavelengths tells us about what's happening in the solar atmosphere, the photosphere, the chromosphere, right up to the corona. You can see here at the 171 wavelengths, we're seeing hot plasma along magnetic field lines. We go to 193 angstroms. What we're seeing here is the darker regions, the coronal holes, the cooler plasma, the filamentary structures along the top of the solar atmosphere. And then when we go to higher wavelength, 131 angstroms, what we see here highlighted are the active flaring regions. And so this sort of brings me on to talking about active regions on the sun, something which we see on the surface at continuum wavelengths as these dark regions or sunspots. And these are regions on the sun where magnetic fields emanate. So they're coming out from these regions. Hence they're slightly darker and lower temperature. And this is where we observe a lot of the activity on the surface of the sun. So flares and coronal mass ejections can originate from these regions. That is because, as we saw in the 171 angstrom, we have a lot of magnetic field lines here. So a lot of activity on the surface. So what is this activity? I'll break it down into these two main regions. There's lots of different activity on the sun, but the ones that we're interested in primarily, and in my research, is flares and CMEs. This is an EUV mixed image, so all of the wavelengths I showed above combined, showing an X-class flare from the western limb of the sun here. And you can see these are incredibly bright, energetic events. These flares are releases of electromagnetic radiation, which we can observe across the spectrum. We observe it with instruments at the X-ray level. Here you can see extreme ultraviolet. Sometimes on the sun, we see white light flares. These are very dim in white light, so they barely affect the overall brightness of the sun, but when extremely energetic events, we can see an increase in the optical. And of course, radio, which I'll talk about in a little bit. But just to show the scale of these events on the sun, if we were any closer as the Earth, these events are absolutely enormous. And for planets orbiting very close, like say Mercury, these have incredible impacts on any weak atmosphere that can exist around them. And that's important to talk about for later. So the other main type of activity that we see on the sun are these coronal mass ejections. These are linked to the magnetic reconnection events of flares, but they can also be independent events. And this is where large releases of plasma are flung off from the solar corona out into interplanetary space. And so what we see here is the AIA image in the center, and then this is a LASCO coronagraph, so blocking out the sun. This was overlaid afterwards. And then you get these huge big loops of plasma, which can shoot out at hundreds of, or sometimes thousands of kilometers a second. And again, we can observe these across the electromagnetic spectrum. Here's just another time-lapse event showing this coronal mass ejection happening. You see these lovely loops and the sheer scale of it in relation to the sun. So that's just to show, further out again. And these events can reach the Earth, which I'm going to talk about in a little bit. But just to show how these kind of events happen in a little diagram, you have flares, which are these magnetic reconnection events. So the magnetic fields snap together and they release energy in the form of electromagnetic radiation. And sometimes when events like magnetic reconnection occur, they catch these large blobs of plasma from the solar atmosphere and they release them into space as a coronal mass ejection. And this releases X-rays down towards the magnetic foot points. And I did highlight here that it emits radio emission at this sort of magnetic reconnection event where particle acceleration is occurring, electron acceleration in particular. But in reality, we really have radio emission from all points of these events, where you can have gyrosynchrotron, high frequency emission down towards the foot points of the magnetic loops, all the way up to ECM here in the center, and plasma emission further out. So these are really good particle accelerators. And what we have are electrons being accelerated mildly relativistically and highly relativistically, generating radio emission in particular across the spectrum. To show an example of this emission, what we have here is frequency of emission, particularly radio we're looking at now, the height above the surface of the sun and how far away it is from the solar surface. And you can see that when we start out at these higher frequencies, these shorter wavelengths, we get a particular type of a radio emission, gyrosynchrotron. As we move outwards to lower and lower frequencies, we get different types of emission based on where the electrons are being accelerated. And it's also occurring in different regions of the solar atmosphere. So you have the chromosphere out into the low corona and the upper corona as we move outwards towards the Earth. How do we observe these kinds of events on the sun? How do we know that it's emitting radio emission? And why do we care? So to start, how we observe the sun at these low frequencies and why it's important, I'm going to bring in, of course, LOFAR, the low frequency array, a fairly recent telescope that has been constructed in Europe, which observes in the low frequencies from 10 to 240 megahertz and has the capabilities to observe the sun at very high temporal and spatial resolution. Here's just a short diagram showing you all of the current and planned LOFAR stations. We have one here in Ireland. The primary core is located in the Netherlands, where you guys are in Astron. Then we extend outwards across all of the countries, and you can even see your one planned in Bulgaria. I think you guys have 3 stations planned there, actually, if I'm correct. Maybe you can correct me on that later. So this enormous baseline using radio interferometry, connecting all of the antennas that we have situated across Europe, gives us a radio telescope with a baseline of 2,000 kilometers, or an effective collecting area of 2,000 kilometers. And we need this at these low frequencies to get high spatial resolution of the sky and the sun. So as I mentioned, this is one of the stations that we have in Ireland, the Irish Low Frequency Array. This is an international station. We have the high band antenna here on the left, observing in the higher frequencies from 110 to 240 megahertz. So that's about 10 to 3 meters. And then we have the low band antenna here, which observe all the way down to 30 meters, which is 10 megahertz up to 90 megahertz. And we have the capabilities to produce images of the sun with the entire LOFAR array, or the core and remote stations in the Netherlands, or dynamic spectra. Then we also have other telescopes observing the sun, of course, across the world. Some that I'd just like to highlight are NONCE and the NONCE radio arrays. They have a LOFAR station also in Nancy in France, but they also extended their low band antenna, and that's what you see here on the bottom. This is called Nenufar, an extension to the LOFAR array, and they have thousands of low band antenna spread out to observe at those lower frequencies where it's more difficult to get higher spatial resolution. They also have the Nancy radioheliograph, which is a large number of antennas, which the number escapes me, in a sort of an L-shaped configuration, which is constantly observing and imaging the sun at very high angular resolution. And then they have a single dish, one of these Nancy radioheliograph antennas was put aside and used as the Orphei solar radio telescope. And what this is doing is always observing the sun, but with low spatial resolution, so it's only producing high cadence dynamic spectra. And I'll talk a little bit about dynamic spectra. Where's my cursor gone? Yeah, I'll talk about dynamic spectra in a moment. But what do we see the sun as at radio frequencies? So I've showed the EUV, very, very high resolution, extreme ultraviolet images. But when we move down in frequency, down in frequency and wavelength, up in frequency, down in wavelength, what we see is the sun is getting a bit more blobby, sort of lower. It appears as if it's getting fuzzy. This is actually inherently due to what the region of the sun that we're observing. So we're now moving upwards, the upper chromosphere to the lower corona, and then into the upper corona in these further images here, produced by Peijing Zhang. And so what you're seeing then is these different electron acceleration regions on the surface of the sun and into the corona. So active regions which are visible at higher frequencies, which will correspond overlay to active regions, say in continuum imaging and in extreme ultraviolet. As we move further and further along, we start to see these electron acceleration regions in the corona. And this will give us an idea of the processes that are occurring and what activity that it's linked to. Now I want to talk a little bit about dynamic spectra, because this can tell us a lot about electron acceleration and the actual processes which are occurring on the sun and how we link them. So we have here dynamic spectra, basically showing frequency versus time. So over 25 minutes and over frequency range of maybe 400 megahertz. And what you'll see are these particular types of structures, which I will show in a real dynamic spectra in a moment. But these are characterized. So we have type 3, these very vertical, bright, very short duration events, which are electrons accelerated along open magnetic field lines from the sun. And then you have these rare type 5 events, which I won't talk about too much, and a very clear signature, which you can see in dynamic spectra when they occur, are these type 2 events. They're very unique. And these are these drifting structures, typically characterized by a fundamental band at lower frequency and its harmonic produced at a higher frequency. These are primarily produced by electrons accelerated by a shock front driven by a coronal mass ejection. So the electrons get shocked and then accelerated, producing this fundamental and harmonic band of emission known as a type 2. And then afterwards, you can get sometimes what's known as a coronal mass ejection afterglow. This is a broad band diffuse emission known as type 4. And I'll talk a little bit about that when we come to stars. But just to show what this looks like from a real dynamic spectra, this is just from a single station, the ILOFAR array, and then at higher frequencies. So we have ILOFAR, apologies, from 10 megahertz to 240 megahertz, which is 30 meters to about 3 meters in wavelength. And then moving further down, we have the Orphei radio telescope, the dish, which is in Nancy. That goes from about 144 megahertz to a gigahertz, so down to about 30 centimeters in wavelength. And you can see all of these sort of events that I mentioned in the previous diagram, these very fast, rapid type 3 events, so electrons being accelerated along these open magnetic field lines. You can also get these higher frequency, very energetic, impulsive type 3s. And then you have this very nice type 2 structure here. So you have a coronal mass ejection, which has occurred. The shock has been able to go super alphenic. So we have the acceleration process, the emission, the plasma emission can go super alphenic. You get a shock, you get electrons accelerated along this shock front, and you get this nice dynamic spectrum of a type 2 across the frequency bands. And this lasts for maybe about 10 to 15 minutes. Then afterwards, what you see is this sort of very diffuse afterglow emission. And if you were to image this, sometimes there's two different types. You can have a stationary emission, which is where this is being produced by electrons accelerated at the foot point. So right at the active region where the CME originated. Sometimes it can be produced by electrons trapped behind the shock front. So you have stationary type 4s in the case where they're at the foot point, and moving type 4s where they get trapped and accelerated along behind the shock front of the CME. So I just have these highlighted here. Forgot I had done that, sorry. What we can also then do is compare these dynamic spectra to times when they occur on the sun. So what you have here, this is work by Maguire et al., is an event imaged in extreme ultraviolet. And you can see a coronal mass ejection on the limb of the sun as it moves outwards. So it's propagating away from the surface of the sun. You can then compare that to the X-ray emission. So that's right at the active region of the sun. And then the radio emission. So you can determine using this, the height and the location, if you have radio imaging, of where the shock went superalfenic and where accelerated electrons to produce a type 2 radio burst. What I'm showing here is radio imaging from some work that we're doing in prep along with the dynamic spectra you saw earlier. This is to show imaging at radio frequencies. This is 150 megahertz overlaid with AIA, so EUV difference imaging. And what that's highlighting here is the moment after a coronal mass ejection has occurred, you can have an event known as an EUV wave. So this is the sort of like the footprint of a CME shock propagating along the low solar corona. And what you get then, you can see by the radio imaging, is that there's radio emission occurring along the sort of footprint of the CME. And so as the shock propagates outwards, you get this beautiful electron acceleration and radio emission in both directions from the active region and from the CME. So radio emission at this high spatial resolution gives us a lot of information into electron acceleration around the sun. It's also a very good diagnostic for where we can be sure that a coronal mass ejection has occurred in this event. We have a lot of other signatures to tell us when a CME has happened on the sun, but this becomes more useful when we look at other stars. Why do we observe the sun across these electromagnetic frequencies, in particular in radio emission? Well, this is very important for space weather. Just check my time, apologies. So space weather, why? So with the sun being so close to us, it directly impacts life on Earth. If we didn't have an atmosphere, life would never have formed. So we have to be very aware of the sun's activity and how it impacts the atmosphere. So when, say, a flare or a coronal mass ejection happens, you get this massive release of either electromagnetic radiation or highly energetic particles. These can damage satellites in orbit completely. So essentially you can have, say, in low Earth orbit, when you have a coronal mass ejection, these particles ionize the atmosphere even further. The atmosphere increases in size. That creates more atmospheric drag that can pull down satellites. You may have heard about that with the SpaceX satellites a little while ago. It can also impact power grids, causing power surges, and this did happen a few years ago in Canada, where it can knock out large swaths of the power grid. We also have to be very aware for astronauts in space and for planes, because it can massively affect GPS. So we always have to be observing the sun across the electromagnetic spectrum for this space weather reason. So now I'm going to move on to sort of the more primary focus of my research, which is M-dwarf stars. I've compared here, let's just start this animation as well, the sun with an M-dwarf to sort of give you an idea of what an M-dwarf is. So an M-dwarf or M-dwarfs as a type of star are characterized by low mass, low temperature stars. So they're often less than 60% to about 10% the mass and radius of our sun. They are also highly convective. So in some cases, they have no radiative core, and they're just about able to fuse hydrogen. So their lifespan is often longer than the age of the universe when estimated and extrapolated. So we expect M-dwarfs to be some of the last stars to exist in the universe for this reason. Along with being highly convective, many M dwarfs are rapid rotators, in some cases orbiting or rotating in less than a day. So this high rotation rate coupled with highly convective cores means they're incredibly active, thousands of times more active than the sun. And so there's a number of ways that we know this. If you look at sunspots on the sun, you see these tiny little dark regions. They only cover a fraction of a percent of the solar surface at any given time. But on M dwarfs, this high convectivity and high rotation rates generate these massive magnetic fields, often on a global scale of kilogauss, which is thousands of times larger than the sun. And these magnetic fields, when they're emanating from the surface of the star, produce enormous star spots, which can cover up to 20% of the stellar surface. And why we're sort of interested in M dwarfs, there's a number of reasons, but this is just an interesting fact that the M dwarfs are the most populous star in our galaxy and indeed the universe. They make up about 70% of the stellar population. This is just a Gaia 100 parsecs of nearby star sample, and there are these often at the end of a HR diagram. There's this huge region where there's just all M dwarf stars. So because they're sort of very low mass, it doesn't take a lot of energy to form them. They make up a massive amount of the stellar population, and they're very long-lived as well. So how do we observe these M dwarfs? How do we know that they're incredibly active? Well, in optical wavelengths, from about 600 nanometers to 1,000 nanometers, we use a spacecraft called the Transiting Exoplanet Survey Satellite. This was launched by NASA, I believe, in 2016 or 2017, aboard a SpaceX rocket, Falcon 9. And its mission, if I play this video, is to observe as many M dwarfs as possible, primarily to search for exoplanets. And it does this by having an absolutely incredibly large field of view. It uses 4 cameras, each with a 24 by 24 degree field of view. So this is the animation showing it here. Allowing it to have a 24 by 96 or 2,300 square degree field of view across the sky. I'll play on. And when you have these cameras and tests in space, it's observing one of these sectors with these 4 cameras every 26 days. And if we skip on again, oh, why is it playing the same video twice? Apologies. Here we go. So it observes one sector of the sky every 26 days, and then it moves on to the next sector. It does this in one hemisphere for 1 year, starting at the southern hemisphere and moving to the northern hemisphere, which in 2 years gives it a sky coverage of 85%. This is the mission moving on from Kepler, which only observed very small fields of the sky. And because TESS observes in this slightly redder region of the spectrum, it is capturing the light from hundreds of thousands of M dwarfs. And it measures the brightness of each star at cadences ranging from 20 seconds to 120 seconds. And in some cases, only 10 minutes, but now moving down to all stars in its field of view will have a light curve of at least 3 minutes. So what do you see when you look at the light curve of an M dwarf? There's a couple of things. I'll first draw your attention to this plot on the right, where you see, as you observe one M dwarf star over a month, you'll see its rotation rate, which is incredibly rapid. But the reason you can see it so clearly is because you see these large dips in the light curve very periodically. This is a gap from a data downlink, and then it continues on again. These very periodic dips in the light curve. This is not produced by planets as I have here, but rather star spots. So those darker regions of where magnetic fields emanate. So this is evidence to show us that we have these enormous magnetic fields coming out of the star, and they're so, the star spots that are created are so large that they're actually affecting the brightness of these stars at some discernible level. We don't detect this on the sun. The sun's optical continuum light curve is flat almost all the time. And another thing that we see when we observe TESS, which was its primary goal, was to search for exoplanets. And exoplanets, when they cross in front of M dwarfs, because they're so much lower mass than the sun, they orbit much closer and the star itself is smaller. So the planet creates a much larger dip in the brightness of the star, a detectable dip, which we can measure, and this is seen in this light curve by this little region here, and zoomed in, you see this transit of an exoplanet, which gives TESS its name. That was the primary goal of TESS, was to search for exoplanets. But another thing that became very quickly apparent that we also saw in Kepler was stellar flares from these M dwarfs, the activity levels of M dwarfs. So what you'll see again are very periodic dips. There's actually two star spots, very large star spots on this star, which is CD56. But interspersed are these massive brightness increases. And these are optical brightness increases, something we don't see on the sun. Increasing the brightness of the star sometimes by over 10%. And these are the stellar flares, the massive magnetic reconnection events occurring on M dwarf stars, which are so bright that we detect them in optical regimes. So this is what makes M dwarfs so interesting. Their stellar activity is so high that we can detect the flares at continuum wavelengths. So when we understand the activity of the star, we want to try and get a better understanding for what the surface of the star looks like. It's impossible to resolve an M dwarf as we do with the sun, but we can do nice little tricks to try and better understand where star spots are and the size of the magnetic field on the surface of the star. And we do this by a couple of methods, but primarily we use Zeeman Doppler imaging. This is where we use spectroscopy to observe the star and sort of observe the change in the polarization and the redshift or blue shift of a particular spectral line linked to the magnetic activity levels. And we can map over time the surface of the star using these spectral lines. So what you'll see here are regions of increased magnetic activity. And then as the star rotates, you see that there's lower regions and then back to more increased regions. And we can combine this with the optical images that I showed previously to create a map of the surface of the star, to sort of try and get a rough understanding of where these star spots lie, how large they are, and the magnetic field strengths around them. And this sort of reveals these intense kilogauss magnetic fields around the surface or around the star spots, which I mentioned, and their large size. This is a very cool technique. I won't talk too much about it, but this is basically how we know that we have large star spots with high magnetic fields around them. So I've talked about M dwarf flares, as you can see, these very bright events in optical, but what about coronal mass ejections on M dwarfs? This is kind of a gray area and something that needs a lot of research at the moment. There have been a lot of simulations done to try and understand how can a coronal mass ejection occur on a star with kilogauss magnetic fields across the entire surface. There's a problem that inherently sort of shows up when you try to determine if a coronal mass ejection can occur, and that is, can a shock ever be formed? Can the plasma release ever become super alphanic and reach a region where it's accelerating electrons to produce, say, radio emission, for example? And so there's been a lot of work done on this. You can see some simulations here which are trying to show how plasma would be released from the surface of the star in a coronal mass ejection event, and where emission may occur from these stars at various frequencies, and where electron acceleration may occur. I'll just play these videos in order to sort of give you an idea of why we may think coronal mass ejections may not be possible on M dwarfs. This first animation is showing a coronal mass ejection as if it was allowed to propagate from the sun. You get this huge release of plasma. It very quickly forms a shock and propagates all the way outwards into solar environment and into interstellar space, interplanetary space. The next video, which I will show, is a partially constrained coronal mass ejection. This is kind of what we hope is the most promising simulation for these M dwarfs, because what this is showing is that initially the plasma, as it escapes, cannot become superalphanic to form a shock. But further out in the solar corona and stellar corona, at perhaps 10 or 20 times the radius of the star, it suddenly becomes superalphanic. It suddenly forms a shock and you get this coronal mass ejection. This gives us hope for detecting radio emission from these stars at lower frequencies. Because if you remember that plot that I showed earlier on for the sun, as you get further away from the star, the emission that you detect becomes at lower and lower frequencies. So it's the same with these stars. The final event, which would be very sad if this was the case, is that the magnetic field is so strong that it completely contains any event from ever forming or ever becoming superauthentic. So you never get coronal mass ejections from these stars. You never get plasma release. It's always confined by these intense magnetic fields. But we can't just rely on simulations. We always need observations because these stars are incredibly dynamic, and not all of these M dwarfs may have intense magnetic fields. There may be regions where the plasma can escape and times when it can escape. So we always need to move to observations. The most promising kind of observations that we have for detecting both flares and coronal mass ejections from these stars, and better understanding the electron acceleration process and potential plasma release, is low frequency radio emission. This is a small sample of M dwarfs that have been detected using LOFAR. This is work from Callingham et al. In 2021. They detected 19 M dwarfs from about 20% of the northern hemisphere using the LOFAR Sky Survey. And so what you can see here, what I've overlaid in the background is the solar image from earlier at approximately the same scale in the skies, let's say. So you see these huge, hopefully you can make this out, but there's these huge regions of radio emission from the sun, and then an equivalent region of the sky in size would show an M dwarf as just a few pixels. This is all of the information we have to work on for these M dwarfs. There's just a few pixels in the sky. So we don't have any spatial information. We can't tell if the radio emission is coming off of the sun due to a coronal mass ejection. We have to rely on the characteristics of the radio emission itself to tell us what's going on these M dwarfs. And if there's other work, if you'd like to investigate this further, by Joshua Pritchard et al. At higher frequencies using the ASCAP telescope, which I'm going to mention in a little while. So what does a dynamic spectrum of an M dwarf look like? I showed dynamic spectra from the sun, which showed bright type 3 bursts, type 2 and type 4 emission, which is indicative of a coronal mass ejection. But what does radio emission look like from these M dwarfs across frequency and time? You'll see this shock, or not this shock, I shouldn't use that word because it's not a shock, but this radio emission detected by Callingham et al. From LOFAR again at about 170 megahertz. And what you see here is emission that looks very different to something that we'd see on the sun. This is long duration emission over almost 3 hours, quite broadband. There's some fine structure in here. But what's interesting about this emission is that it's highly circularly polarized. And this is where I have to bring in the characteristics of the radio emission. What we see on the sun is often low circular polarization, low brightness temperature, which means it's primarily plasma emission or gyrosynchrotron from the sun. But when you get to these intense magnetic fields from M dwarfs, the electron acceleration is much higher. And what you primarily see is electron cyclotron maser emission, a beamed form of radio emission, which is highly circularly polarized and very, very energetic. And so what you're seeing here is perhaps a beam of this radio emission as it is detected by LOFAR over time. But is this evidence for a coronal mass ejection? A different type from the star? We don't know. We need more information. This is more dynamic spectra of an M dwarf just to show how different it looks to the sun. Perhaps this looks slightly familiar, maybe like a type 4 burst, but there's this interesting sort of drifting structures throughout it. This is taken from the Very Large Array in New Mexico. This is highly circularly polarized emission and lasts over a very long period of time. So almost an hour and a half. And this is at gigahertz frequency. So we're seeing this radio emission at both low and higher frequencies, but we still don't fully understand its origins. If it's in some cases related to flares, if it's quiescent emission that's always occurring, not linked to optical flaring, or if it is perhaps evidence of coronal mass ejections from these stars. Some of the most promising information that we have, or promising data that we have at radio frequencies of evidence for a coronal mass ejection, is what this dynamic spectra that you see here. This was taken with the Australian Square Kilometre Array Pathfinder telescope, and it's an observation of Proxima Centauri, our nearest star. It's a very active M dwarf. And so I'll bring your attention first to this optical light curve taken by TESS at the bottom, which shows a very high energy optical flare. And this was observed also with other spectral, other wavelengths, hydrogen alpha and the G band. But what this is showing is that the brightness of the star was increased by 60% during this flare event. So incredibly energetic flare. But they were also observing with ASCAP, so ranging from about 1 gigahertz to 750 megahertz. And you see this first impulsive radio emission directly related to the flare. And afterwards, this more diffuse broadband emission, which looks quite similar to type 4 radio emission, perhaps at higher frequencies. And then if you see the light curve for this, you will notice that the Stokes V shows that it's a highly circularly polarized emission, again, probably electron cyclotron maser. But this sort of faint diffuse radio emission after an optical flare is perhaps evidence for a stellar coronal mass ejection from Proxima Centauri. But as ever, we can never just use one star or two stars as evidence that these events occur. We always need more data. And one of the benefits of the ASCAP telescope is its enormous field of view. So it's observing, the ASCAP, to give a bit more context to what type of telescope it is, it's a 36-dish interferometer in the Australian outback, observing from 700 megahertz to 1.8 gigahertz across a couple of different bandwidths. It observes the sky at 1 second cadence with a 36 square degree field of view. That's absolutely enormous. So it's primarily a survey telescope for that reason. And back in, when was it now? August of 2021. Maybe 2021, yeah. We had, no, it was May of 2021. We had 26 hours of observations with this telescope to do a bit of research and to search for radio emission from M dwarfs. But in this instance, unlike the Zick et al. Paper, which focused on one star, we wanted to use ASCAP's enormous field of view to try and sort of get the best time, the best benefit from the time that we had, and try and detect radio emission from many M dwarfs at once. But we also wanted simultaneous optical emission. So we again turned to TESS, which I'll talk about in a moment. But here is a little diagram or plot showing the size of ASCAP, just with the full moon, the beam layout from each of the antenna, and the incredible resolution that you can get. You can just zoom in and in and in on this image, and you'll see primarily a lot of extragalactic emission or AGN, so emission from other galaxies. This is some of the, I believe, small Magellanic Cloud, the diffuse hot gas emission. But there's the full moon. So this field of view is 6 by 6 square degrees. And what we wanted to do was get some optical observations, and that was look for flares from these stars at the same time we were searching for radio emission. So you can see what I've done here is just quickly overlaid the ASCAP field of view over the TESS field of view that I mentioned earlier, which is 24 by 96 degrees. So we had no chance of observing the whole region at the same time, but this is probably the best you can get with radio emission and optical emission simultaneously in a large region of the sky. TESS was observing in sector 36 in the southern hemisphere at this time for 26 days, and we had 24 or 26 hours simultaneously. These are the results of our observations in this case. This is the radio images from the ASCAP telescope of M dwarfs that we detected in the field. And what you'll notice is here, so the top two have no circular polarization, and the bottom two have very highly circularly polarized emission. And this is, again, telling us about the emission characteristics of these stars. And this is very important because we also had optical emission. We wanted to see if we could correlate this with a flare. And what I'm showing you here is just the optical test light curves from two of these stars. And what, again, you'll see is that they have very large star spots on their surface. So this one, very, very periodic single star spot. It's also quite not very active at all, having only a couple of small flares, relatively small flares during its event, during the observations. Excuse me. And then on the top one here, what you'll see is that it has a number of star spots. There are 3 or 4 on this star. It rotates every 0.8 days. and it has very highly energetic flares in the optical. But the region that we co-observed with ASCAP is highlighted here in orange. And what you'll notice is there's only one event which just barely overlaps with the radio observations. And this region at radio frequencies was impacted very highly by RFI, so we had to actually discard it. So when you zoom in on these regions, you'll see that that flare is here, but we did not have radio detection of the star at that time. However, there was some interesting optical brightening event that doesn't match a flare profile from the star, where we detected radio emission peaking at the same time as this event. So this is the flux of the stars. These are incredibly faint detections. The sun, for example, is what, tens of thousands to maybe hundreds of thousands of Janskys. You don't ever need to worry about the flux units of the sun because it's always there. It's always detectable. But on these stars, they're incredibly bright on the millijansky level. So just getting a detection is a good thing. And we actually detected an increase in brightening during this event. And then on the other star, there was absolutely no flares at all detected at optical frequencies. But we had a very clear radio brightening with ASCAP. So this is very interesting. And both of these events at radio frequencies had no equivalent circular polarization. So this is perhaps gyrosynchrotron emission, maybe even plasma emission, from these stars that we're detecting without simultaneous optical flares. So this is another avenue to explore with these M dwarfs. What else should I say about this? No, I think that's pretty much everything. So I just want to briefly highlight that there are other ways to search for CMEs other than radio emission. This isn't research that I do, but it does exist if anyone's interested. I just wanted to highlight it, that you can also use spectroscopy at X-ray wavelengths to search for Doppler shifts. So particularly Doppler blue shifts of X-ray lines, which show plasma and moving towards the observer, which might be evidence for plasma being released from these stars. And in turn, a coronal mass ejection. There's some promising work that was released by Armagh et al. In 2018, just showing this sort of a potential signature that this plasma emission occurred or plasma release occurred. The research that we conducted with ASCAP and TEST is summarized in far more detail in a paper that we published earlier this year. If anybody would like to have a read of it, I've left a QR code here and a link to the paper. And just to highlight for that research that we were able to utilize the wide field of view of ASCAP in 26 hours to detect 4 M dwarfs at radio frequency with simultaneous optical emission. This is very promising, especially going forward, now that the Transiting Exoplanet Survey satellite, now that TESS observes its full field 24 by 96 degrees at 3-minute cadence. So you get brightness on all the stars detected in the field every 3 minutes, which is enough to detect an optical flare. And so with telescopes like LOFAR, with its wider field of view of 2 degrees at high frequencies, and ASCAP and other telescopes around the world, we now have the potential in a single observation to detect emission and explore the emission from these M dwarfs, from many M dwarfs at once. And this perhaps will give us the chance to correlate the radio emission with optical emission, or perhaps without optical emission, which is even more interesting for the detection of stellar coronal mass ejections at radio frequencies. I think I'm almost finished. I hope I haven't run over, or maybe I have a little bit. But the reason why we're so interested in these stars is exoplanet habitability. M dwarfs, we've detected most of the exoplanets that we know around low mass stars due to their suitability for detection via the transit method and via radial velocity. So we know thousands of exoplanets that orbit M dwarf stars, but we don't fully understand the stellar environment around them. And we really want to know if the activity from M dwarfs can potentially strip away the atmosphere of an exoplanet. You saw how coronal mass ejections affect life on Earth, but imagine an event thousands of times stronger on a planet orbiting closer than the orbit of Mercury to an M dwarf. And if these events are occurring frequently, then we may need to look at redefining habitable zones, or also perhaps redefining how life itself forms on these planets. There's some very interesting work that I'll leave here by Cavan et al. Simulating the potential for detecting planets via the interaction of radio emission with its host star, similar to the Jupiter Io system. And there's been tentative work to try and detect this by Vedantam et al. On the right here. But the sort of summary of all of my research is that stellar CMEs, where are they? Or what is trying to understand radio emission from M dwarfs by first understanding emission from the sun and then scaling it up. So I think I'll leave it there in the interest of time. If anybody has questions, I'm happy to answer them online and offline. My Twitter's there, my email's there. That's everything. Thank you. Hello?
Can you hear me now? Hello?
Now I can hear you.
Okay. So thank you very much. I have a lot of questions. I don't know about others. Maybe I can ask a question first and then we can open the floor. So this is all very interesting. It seems to me like there's two clear classes, let's say, of stellar flares based on the energy. The fact that you don't observe that you observe radio emission when there is no flare in that latest result, which could be gyrosynchrotron, could be plasma emission, like the standard emission types for solar activity, right, in the radio. But there is also this very bright, very collimated and polarized emission from the maser mechanism.
Yes.
Could this be just two different? I mean, could you always have? What I'm trying to say is, could the M dwarf activity be just like the solar activity, but then on top of that, you could have these very, very much brighter episodes when you have the optical flares that correspond to the maser emission?
Perhaps. I think in some instances, there are so many of these M dwarfs that we're still even just detecting them at these frequencies. But there are some M dwarfs with lower magnetic field strengths, maybe closer to the sun, and perhaps there are regions on these stars that may have magnetic field topologies which are similar to that which we see on the sun. I mean, we still haven't conclusively detected these types of emission from these stars, but if we do, that provides a momentum to detecting potential coronal mass ejections. The other thing that is interesting about M dwarfs that we don't see on the sun as much is auroral emission. So because of these intense magnetic fields, you get emission a lot, depending on how the star is oriented to Earth, from the poles of these stars, and that is often the gyrosynchrotron emission, and that can occur without any optical flaring. That could be something which is occurring continuously from these stars, just due to some magnetic interactions at the poles. But yeah, so, it is. Sorry, go ahead.
Well, I was going to, if you could share your screen one more time.
Yes, I wanted of course. Sorry.
See if you've taken into account, maybe go back to where you were showing the dips due to maybe just go back to the previous, towards the beginning when you were showing the time series of the
these ones. I can't remember, sorry.
Yeah, no, going forward.
Hang on, apologies, if I share the actual slideshow, here we go.
Yeah. It was in black, showing the time series of the optical.
Oh yes.
Yeah, this stuff. Yeah. So could there be some special episodes when you would like to observe? For example, what I thought looking at this left plot is that latest big flare occurred at the peak of the optical flux, meaning there shouldn't be the area of the star spots is the smallest, right? So in other words,
yeah.
And that could mean that you could have the flare coming from the limb or something like that. Whereas,
exactly, yes. So this is, I see what you're getting at. Yeah. So this is the issue.
to observe.
Yeah.
So
this is one of the issues, yeah, that these events are actually stochastic. So we have no way to predict where they will occur at a particular star spot rotation regime. Like they may be occurring, like you said, right at the limb. They may be occurring between two enormous star spots that are either side of the limbs that we don't see, but then the event itself occurs Earth facing. And so trying to pick your moment to observe these stars at radio frequencies is very difficult. You can observe the star for a week and see nothing, or you could observe it for 30 minutes and catch this super flare event. But predicting the activity based on the presence of a star spot in a particular region of, say, the rotation rate, I think it's been attempted, but it seems to just not be the case that there's any correlation between location of flare or when to best observe at radio frequencies. If that answers sort of what you were.
Well, I guess my suggestion was that you could possibly say something about their topology as viewed from the Earth. If you observe something in radio, you could add a little bit more information by looking at the optical, the position there as to when this was done. And my last question, and then I guess Tony will say something. But my last question is: these simulations that you showed, they seemed, the magnetic field seemed very symmetric. I mean, how can this be if you have these enormous star spots on one side of the star? I mean, I imagine like a regular magnetic field here and then something humongous on the other side. This looks like the Earth's magnetic field.
Yeah, I suppose they're probably still, I haven't looked too much into these simulations myself, but we're still very limited on how we can understand the topology of these stars. Even the ones that I show you in Zeeman Doppler imaging, it's only the connection between a couple of large star spots. We don't have perfectly spatially resolved information on the surface of these stars. So creating a complex PFSS model like you would on the sun just isn't really possible. Now, as for exactly how they choose where to place magnetic field lines on these models, I'm not quite sure. Maybe you can see they just choose a few small field lines to reconnect to initiate the plasma release and the flare event. But yeah, I agree that in some cases these do appear quite symmetric. I think the intention in these simulations is to show that no matter how the configuration, if the global magnetic field strength is a kilogauss or 1.4 kilogauss, it will just completely constrain that plasma. It will, in no configuration, will allow it to be released. But I don't understand them completely to be able to give a full answer. But the best research to read about that will be Alvarado Gomez or Dualto Fionagon. Their explanations of their simulations are brilliant.
Thank you very much. Tony?
Hi, Jeremy.
Hello.
Very nice talk. First, a comment about Kaman's first question. You would look to observe a star where a flare happens, but in the radio, but that means, or you presume that the radio emission is connected to the flaring emission from the star, or could be a completely different mechanism that doesn't depend on the flare itself. It depends on the magnetic activity, but it's not connected with the flare. And this is happening in the outer corona, then the flares are irrelevant. But even the statistical studies from Kepler and TESS show that there's no connection, for example, between spots and flares. So it's difficult to predict. Yeah, my question for Jeremy after this comment is something else. Have you tried to think about or to look in the ASCAP data for stars that are actually not that active? M dwarfs that have slower periods of rotation and are not that active.
So the fields that I looked at just for our research, those were the only overlapping M dwarfs that had test light curves. But I know that the survey done by I mentioned it earlier, the name has gone out of my head.
Well, one was
sorry.
Joe Callingham and Harish Vendatam. You mean those surveys in LOFAR?
Oh, yeah, but even there was an ASCAP survey done, if I can find it. I mentioned it. Oh, yeah, Pritchard et al.
Yes.
So they have that is a survey of the Southern Hemisphere. It's a not a deep sky, not a deep survey, but a very quick survey of the sky where they detected, I believe, 11 or 14, one of those numbers, M dwarfs in their survey. And I didn't check to see if some of those were quiescent, but I haven't gone back to check our data in more depth because we were primarily interested in searching for that test simultaneous light curve. So the only 4 that we detected with test light curves in our data were the 4 that I showed. But as for quiescent M dwarfs, there may be some in that data.
Yeah, so say M dwarfs that have longer periods do not show any flaring activities in the optical, or very, very little flaring activities, longer period, lower activity levels. Have you tried to look for emission from them in the ASCAP data?
I haven't yet, no. So that would be something to
something you need. Research. I think something you need to have a look at. Just
definitely, and also
you know why I'm asking that question.
Yeah, yes, definitely. And the other thing that I had mentioned just on that note was that other spectral types of stars, because we look at M dwarfs all the time, but there's also K dwarfs and brown dwarfs, which perhaps are active at radio frequencies, but are very quiet and optical and very hard to detect. So yes, that is definitely an avenue to explore.
Yeah. Thank you. Thanks. My other question for Jeremy is private and it's going to be after that in an email, I guess.
Okay.
So.
But Tony, can I follow up? What would you say about those magnetic fields? Is the global magnetic field so large on the M dwarfs that you don't expect any big asymmetry when you have a humongous star spot on one side? You wouldn't expect like a big asymmetry in the magnetic field?
I wouldn't understand how they go about estimating the topology well enough. I would imagine there would be quite a lot of asymmetry if there was a large star spot on the surface. But as for how that plays out, I mean, even we don't fully understand that these enormous star spots are actually hundreds of smaller star spots. We don't have that kind of resolution. So to try and estimate the magnetic field strength just based solely on what we know so far is very difficult. But all we know is that they cover large regions and they are intense. So I guess the best simulations are these symmetric models, but they're definitely not at the level of accuracy that we can call them confident. You know, they're very much based on estimates for now.
Yeah, but I mean, you can simulate everything.
Yeah.
No, just see what
you can simulate everything. How close is it going to be to the truth?
No, I mean, that's not the point. The point is you want to gain some intuition as to what these things should look like, not necessarily to represent a particular star, is what I'm saying.
Yeah, but that's the thing. The question is how connected is, for example, the radio emission to the spots and the spot coverage. You have the global magnetic fields when you're especially at low frequencies, what you detect is mostly coming from the outer corona. It's not emission that originates close to the disk, to the star surface. So what you're interested in is the magnetic fields that are further from the star. And most of these very active stars have global axisymmetric magnetic fields. What you said is very similar to the Earth is expected to be.
Okay. Yeah, that's what I was asking. Okay.
And the other emission that you're talking about that's connected to the flares, I think And the closer to this, what's happening to the surface, you're looking at this mostly in the higher bands, at the gigahertz bands. What's very curious though, is that very recently there were some publications about radio emission from active M dwarfs detected with ALMA in the millimeter band. And that for me is really, really interesting.
So what is that thermal emission?
I don't know.
Super close to the surface, a chromosphere on the star.
Yeah, something's happening there. Could be plasma emission. Most likely plasma emission or very, very high energetic particles again. Something like the electron beams or something, but happening very close to the star.
All right, Mohammed?
Hi, thanks, Jeremy. It was an interesting talk. I have two questions. The first one is how to differentiate between a huge sunspot on the M dwarf and a coronal hole. Is it from the observing frequency, or maybe there is another method?
Yeah, so that would primarily be the observing method. So the star spots that we observe are at optical wavelengths. So that would be that we don't observe coronal holes. They would be at the EUV wavelengths, and we wouldn't be able to detect that sort of oscillation at extreme ultraviolet wavelengths from these M dwarfs. We just wouldn't have the sensitivity. But so that's sort of how we detect or how we see the star spots is in the optical light curves. Yeah.
Okay. And my second question is, when you observe the brightness over time of the M dwarf, and you see this decreasing in brightness, how to differentiate between the decreasing produced by an exoplanet orbiting around the star or decreasing from a huge sunspot? Is it from the periodicity of this effect? Like if it was persistent, so that probably means it's a planet?
That's a great question. Yeah, so this is actually one of the problems with detecting planets around active M dwarfs, is that the star spot modulation, this periodicity that you see here is all due to star spots. And these star spot decreases can be quite large. You can see here that the variation in the star is a few percent just by the star spots alone. Whereas an exoplanet transit can be as small as a fraction of a percent for a very small planet orbiting close. So there's a lot of difficulty in removing star spot modulation from M dwarfs to try and get those exoplanet signatures. What you mainly detect are these very clear signatures where you see here that, first of all, the exoplanet transit is very, very short in duration. So it's only going to cross the star over what you see here, what's this, a couple of hours, whereas these star spot modulations can last for half a day or more. But also it'll be a different, it'll have different properties to a star spot. But it's almost guaranteed that some exoplanets can't be detected around their host stars due to their level of activity and these huge star spots, that they're just getting lost in the noise, so to speak. So that's a great clarification. Thank you.
Thank you very much.
Thanks.
Okay, any other questions?
Ask here.
The microphone's there.
Okay. Hi there. Can you hear me?
Hey, all right.
Okay. So my question is, you mentioned maser emission mechanism that requires low density or extremely strong magnetic field, which is not very commonly existed in the solar case. Is this the case for M dwarf also, or are we expecting strong magnetic field as well as low density coexisting?
So in these M dwarfs, it will almost always be electron cyclotron maser that is detected, and this is due to these intense magnetic fields. And it's almost always this beamed emission, and that is one of the reasons why, say in the Callingham survey that I mentioned earlier, if I go over here, why in 20% of the northern hemisphere, where we detect thousands of M dwarfs at optical frequencies, are we only detecting 19 M dwarfs at low frequency radio emission? And this is likely or potentially due to this beam defect, that we may have the beamed emission never sweeping the Earth, and we may not be detecting a large number of M dwarfs, which are just, we call radio quiet, but maybe radio loud, with completely different magnetic field configurations that we just can't see. So all of these detections you can see in the inlets here are very highly circularly, almost all very highly circularly polarized, which is indicative of this ECM emission. So yeah.
Thank you.
Thanks.
And also the long existing 3 hours,
Oh yeah.
sort of like type 4 moving statical time for. Is this also, you assume it's a major emission also?
Yeah, I believe so. Based on the almost 100% circular polarization and high brightness temperature, I think they concluded that it was likely ECM. If I'd have to double check the paper, I haven't read it in a little while, but it's Zic et al. 2020, Proximus Sen ASCAP tests. I believe, yeah, it was either gyrosynchrotron or ECM for this case, but the high circular polarization and high brightness temperature are often characterized as ECM. So of course, yeah, so in this instance, this is why this is like, so they don't ever conclude that they've seen this as a type 4, because of course type 4s on the sun or the plasma emission, you wouldn't see much circular polarization at all, if any, with the type 4. But in this instance, it is highly circular polarized. So we don't understand the emission from these stars at all. We need to maybe change our understanding when we compare it with the sun. The emission mechanism may be different, but the outcome may be the same.
Yeah, for solar case, there's a lot of depolarization mechanism, like scattering and propagation effects, to bring down this polarization level, like to decrease the circular and linear polarization. But it's interesting that you observe almost 100% polarization, which means the that's what I'm also thinking about. So that the scattering and refraction is much weaker than the solar case.
Yeah, it is right. Yeah, true.
Yeah. Okay, thank you very much.
Thank you.
All right. Any other questions for Jeremy? If not, let's thank him one more time. Thank you, Jeremy, for this cool seminar. And thanks, everyone. There will be more stellar seminars coming up, so you will be notified. And thanks again.
Thank you. Thanks, everyone.
Thank you.
Bye.